Hello and welcome. Okay, let's just jump right in because today we're talking about something pretty wild. It's one of the most unexpected and honestly profound connections in all of modern science. The super deep link between the fundamental laws of physics and the artificial intelligence that is completely reshaping our world.
So it all really kicks off with this headline. A headline that made a lot of people, myself included, do a serious double take. The Nobel Prize in Physics was awarded for work in AI. I mean, come on, that's not something you see every day. And that right there, that's the big question. That's the mystery we're going to solve in this explainer. What on earth does building an artificial brain have to do with the fundamental laws that govern the entire universe? Well, the answer is a fantastic story, and it actually stretches back about a century. Okay, so our first clue takes us back, and I mean way back to the 1920s. This is long before computers as we think of them were even a thing. Back then, physicists were wrestling with this really fundamental property of matter, magnetism.
So you had a professor, Wilhelm Lenz, who posed a problem to his student Ernst Ising. They imagined a material, like a chunk of iron, as just a simple grid of atoms. And each atom has this tiny magnetic spin that could point either up or down. Now, heat makes them jiggle around randomly, but the spins, they prefer to align with their neighbors. And why is that? Well, because that alignment is a more stable, lower energy state for the whole system. It's just calmer.
Now let's fast forward 60 years to 1982. A physicist named John Hopfield has this absolutely brilliant insight. He basically maps these physics concepts directly onto a new idea. So the atoms with their up or down spins, those become artificial neurons that are either on or off. The influence between those spins, that becomes the weighted connections, the synapses between neurons. And this is the crucial part. The magnet's search for a low-energy stable state, that becomes the network search for a stable configuration. In one move, he transformed a model for magnetism into a model for memory.
And to really get this, physicists use this beautiful analogy, the energy landscape. Just picture a marble rolling across a huge mountainous terrain. The marble's exact position is the network's current state, and the altitude, how high up it is its energy. What's the marble going to do? Well, it's naturally going to roll downhill, right? It's going to seek out the lowest valleys it can find. In the exact same way, the Hopfield network relaxes into the most stable, lowest energy configuration it can possibly find.
And here is the absolute genius of it. By changing the weights, the strengths, of those artificial synapses, you can effectively become a landscape artist. You get to sculpt this whole terrain. You can dig these deep wells and valleys around specific patterns you want the network to remember. So then, when you show the network a fuzzy or incomplete pattern, it's like you're placing that marble on a hillside. It just naturally rolls down into the nearest, deepest valley, which is the complete correct memory. It's so clever.
So yeah, the historical link is crystal clear. A model straight out of physics directly inspired the first really functional neural networks. But if you think that's where the story ends, you are in for a big surprise, because the connection gets much, much deeper than that.
Right, because it turns out this isn't just some clever analogy from back in the day. Nope. More recent discoveries have shown a fundamental mathematical correspondence between modern AI and the most fundamental theory of reality we have, quantum physics. It gets weird.
To really get our heads around this, we need to think about a neural network in a slightly different way. So instead of a bunch of neurons and wires, picture it as a mathematical field. Think about a weather map. That's a field that assigns a temperature value to every single point on the map. A neural network is kind of the same. It's a field that assigns an output value to every single possible input.
So back in 1995, one of Geoffrey Hinton's students, a guy named Radford Neal, asked a really strange question. What happens to the behavior of these networks if you just keep making them wider and wider, adding more and more neurons, all the way to infinity? You'd think it would just become infinitely complicated, right? But something totally remarkable happens instead.
And here it is. This is the big reveal. As a neural network gets infinitely wide, the statistical behavior of its outputs becomes a perfect bell curve, a Gaussian distribution. Now here's the kicker. A basic quantum field, the actual fabric of reality itself, when it's just sitting there, it fluctuates in exactly the same way. They both produce a perfect Gaussian distribution.
So this is the point that should make the hair on your arm stand up. It's not an analogy anymore. At a fundamental level, the math that describes an infinitely wide neural network is the same math that describes a basic quantum field. They are literally speaking the same language. This one discovery has just ripped open a breathtaking new frontier for science.
So why does any of this matter?
Well, because if these two fields that seem totally separate are actually speaking the same language, it means they can start sharing tools, and this has created an incredibly powerful two-way street for discovery.
So, first off, we can now use the entire powerful toolkit of theoretical physics to understand AI. Seriously, concepts and tools that were developed to study particle interactions are now being used to peek inside the black boxes of neural networks to figure out why they work. And it goes the other way too. AI is giving physicists a completely new way to tackle their absolute hardest problems. Simulating complex quantum systems is a massive, massive challenge, but it turns out neural networks are an incredible new tool for doing exactly that.
And look, this isn't just theory, okay? This is happening right now, today. AI is being used to find the tiny, faint signals of colliding black holes and gravitational waves. It's hunting for new particles at the Large Hadron Collider. It's mapping the invisible dark matter that holds our galaxies together. And it's even helping us navigate the bizarre, complicated landscapes of string theory. This is nothing short of a revolution in how physics gets done.
Which, of course, brings us all the way back to that Nobel Prize, and it leaves us with one final, fascinating question. We started with a pretty simple model of a magnet, and we ended up here, with AI and quantum field theory sharing a deep mathematical grammar. So, if the code that allows a machine to learn and the code that governs the universe itself are this closely related, what else might they have in common? What other secrets are just waiting there for us to find?